And Stefan, please. Stefan Kaiser from, I think right now from Dresden something. Oh. Dresden Technical University.
Yeah. So exactly. Can you hear me?
Yes. There you go.
And can you see my screen?
Just dark. I probably need to down. Yes, we do.
Maybe I have to go to slideshow. Yeah. Do we have full screen?
No. Click on the first slide.
Yeah, I'm seeing full screen.
Okay.
Okay. Good.
Okay. Yeah. So welcome everyone. Yeah. Unfortunately, only in the online format, but nevertheless, today I want to present our recent advances in the field of Higgs spectroscopy, and today I want to talk on the transient Higgs spectroscopy. And why I don't have the laser pointer here? Okay. Yes. And the idea is that we want to use now the Higgs as a probe. And then when we talk on Higgs spectroscopy and superconductors, luckily Ilyas did already a phenomenal introduction in the first part of the session. And today I want to first highlight the contributions to this work. This was performed within the Max Planck UBC Uni Tokyo Center for Quantum Materials, and experiments were performed in my group back in Stuttgart and now in Dresden. Key players Hao Chu and Min-Jae Kim. This was done in strong collaboration with Ryo Shimano's group at the University of Tokyo. And many of the experiments are performed at the Helmholtz Center Dresden-Rossendorf with the Telbe terahertz high field group led by Sergei Kovalev. And we have theoretical support by Dirk Manske's group and also by Lara in Stuttgart and Lara Bonfatto's group in Rome. And here in particular on the second part, Raphael Hanel, a new student here, did many contributions. Samples came from the group of Bernhard Keimer, and then also samples from Paris were measured throughout many of these projects. And when we talk on Higgs modes, we are talking about these collective excitations in the superconductor. We all know these collective excitations of the lattice as phonons, of magnetic systems, the magnons, of electrons, the plasmons. But then the collective excitations, basically the collective excitation of the Cooper pairs, these are the Higgs modes itself, and they're intimately linked to the Meissner effect in the superconductors. So that is what really is the equivalent, so that the Higgs mode in principle probes the Meissner effect in our superconductors. And we have seen before that when we look at the collective modes in these famous Mexican head potentials of the superconductors, we're dealing with two of these modes. One is this phase oscillation around this rim, and then the Higgs mode is really this amplitude oscillation in this Mexican head. And if we have then the dispersion of these, here we have the Higgs amplitude mode in the system, and these phase Goldstone modes, as we have heard already before, due to the Anderson pseudospin formalism, is lifted up to the plasma frequency in the system. So the lowest stable mode in a superconducting system is this Higgs mode. And if one can excite this Higgs mode, then one would see an oscillation around the order parameter with a frequency of 2 times delta in a superconducting system. The question was then, okay, for a long time, how to excite such Higgs modes, because in principle, what you would like to do is now to shake this condensate. That is something that is very simple for people that work in the cold gases, and there are beautiful experiments where you can observe it. It is quite difficult to shake a condensate. So there, the first idea is to quench the condensate. Coming with an ultra-short light pulse, one quenches the condensate on a time scale fast compared to the eigenfrequency of these Higgs modes. So the system is then in this displaced position and then starts oscillating around the new potential minimum in this case. And there, the pioneering experiments go back to Ryo Shimano's group back in 2013, where in niobium nitride, by excitation with an ultra-short terahertz pulse, they could see really these free Higgs oscillations of the system. And also, as we've seen before, when you increase the pump energy, you quench the condensate more, and that softens the Higgs oscillations in the system, and really following this 2 delta in the quenched state on this system. However, there's also a second way to excite Higgs modes, and this is not to use now the free Higgs modes with an ultra-fast quench, but using the possibility to drive Higgs oscillations continuously. And we have also seen this in the talk before. Here we are going to drive basically the Anderson pseudospin precision of this spin. So if you take a monochromatic terahertz pulse, really a multi-cycle pulse below the superconducting gap, then one can show basically that the superconductor reacts with a 2 omega oscillation in the system. Hand waving, one could say, if we couple the light, we have seen this before in great detail, with the momentum with E times A, for as momentum transfer per electron, so E square A square in a Cooper pair, then we expect a response that goes with A square of the vector potential, and that's the 2 omega response of the superconductor. Moreover, one can show if this 2 omega oscillation, this driven oscillation of the Higgs mode, becomes resonant with the free eigenfrequency of the Higgs mode at 2 delta, then there is an efficient 3 omega third harmonic generation in the system, just driving this nonlinear Josephson current in this system. And so we can take now this third harmonic generation as a signature of driven Higgs modes. However, we are quite interested not in the typical S-wave superconductors, but in the cuprates, which are systems that have D-wave superconductivity. And here, besides the different spectra of the Higgs modes, here in principle we have only the possibility for one type of Higgs oscillations, whereas in a D-wave system, in principle, the spectra can be more complex. The key problem here is that also if we look at the structure of the superconducting gap, that is also significantly different between an S-wave system and a D-wave system, because in a D-wave system, the gap does not fully open. So that means at any given energy, we find quasi-particle contributions in the spectrum. And that means the Higgs modes in the cuprates are expected to be heavily damped, and therefore one would have to use this driving Higgs excitation mechanism that I've just showed you before. And here you can see this in the calculated spectra of such a system, whilst in an S-wave system, you really have a sharp, basically non-damped Higgs mode in a system. For a D-wave system, one would expect a heavily damped mode in these parts. And also experimentally, the first fingerprints for Higgs in cuprates was done in Ryo Shimano's group by Kota Katsumi. And they tried really this impulsive excitation of the Higgs modes. But then, as you can see here, you see something like, here is the square of their driving pulse. You see it's like a single cycle drive of the Higgs modes, but there are no free oscillations in the transient dynamics of this system. So what we did then is we really went to these high field terahertz sources at the Helmholtz Center Dresden-Rossendorf. This is a super radiant terahertz source that allows to really generate very, very strong multi-cycle terahertz fields that are tunable in a range between somewhere a few hundred gigahertz up to 3 terahertz in this system. And with these pulses, we have now performed a Higgs drive experiment, putting in different types of superconducting samples. So our driving frequencies are 0.7 terahertz. So we are expecting a third harmonic generation at 2.1 terahertz in the system. This is now one example of superconducting LSCO optimally doped above the superconducting transition temperature. And what you see here is just the transmitted terahertz field at 0.7 terahertz. If now we cool down the sample below TC, and then you can clearly see here that a new oscillation appears, and this is really the third harmonic generation due to the driven Higgs mode. We can then separate this by filtering these signals into the fundamental drive of the terahertz pulse and the generated third harmonic generation. And then we can analyze this signal in amplitude and phase as a function of temperature. And if we do so in several classes of cuprates, that is something I have shown already on the last conference. That is something where we really saw that throughout the different classes of cuprate superconductors, we find a prominent Higgs response below TC that sets in. And then if you take away the screening, you see also that there is some substructure of the Higgs response even below TC. And this was fully in agreement with our expectation of a heavily damped Higgs mode. And to really learn something about the damping of an oscillating system, it's very instructive to look at the phase, because if you have a resonance frequency in a system, usually you have a pi phase jump exactly around this frequency. And if you have a heavily damped system, you're broadening your amplitude peak and your phase jump starts to soften out. And here you see indeed around TC, basically we have a very smooth transition of the phase. But then to our surprise, back then, we really saw significantly below TC a very prominent pi phase jump. And then we found this throughout these different families of the cuprates. But also, if you compare this with the expectations from a normal oscillator model, this phase jump is not indicating a resonance, but an anti-resonance, which brought us to the conclusion that here we have another mode, an external collective mode that is coupling to the Higgs mode. When we just model this, then we could see that if you model such a coupled oscillator model, then you can really expect a phase jump that matches the experimental observations pretty well. The big question was now how to identify this new mode. And that was something that actually I had planned to show on the live conference in Greece, which now did not take place. But what I can tell you is that our picture points into the direction that this new mode in principle are charge density wave fluctuations that are mediated via phonons in the system. And first fingerprints to such a mechanism can be found already in pump probe work by David Hinton back in 2013, where they saw CDW coupled phonon oscillations in underdoped YBCO from time dissolved reflectivity measurements. And then they came up already with a model of a coupled superconducting and CDW order parameter in such a system. And the question is now, is something like this really happening in our system? But this is not what I want to talk about today. You can find some details in a new manuscript that we just put on arXiv recently. So this coupled mode that we see, we can now really describe really with a generalized Fano resonance of the Higgs mode in the system. And by performing a detailed doping dependence and magnetic field dependence, here I show you the results, what is happening to this sharp phase jump that becomes softened out by going to the overdope regime or by applying a magnetic field. That is pointing to the interaction with a CDW phase in the system. In the talk today, however, I want to show you some new stuff that is not in the paper, and that also emphasizes a little bit the interaction with a CDW in these kind of materials. And what you see here now is again the third harmonics dynamics in the time domain for an underdoped LSCO sample. And then if you look here at a low power drive, everything looks like a smooth THG signal that we had. However, if you go to some intermediate excitation energy, then you see here that somehow there is a notch in the middle of the THG signal. And first we thought, okay, maybe here we are quenching superconductivity because of our extremely high driving fields. And this is really, that was actually what we have measured first. And then we thought, okay, this is really in the middle of the excited THG signal. So this is just the quench of the superconducting state. However, when we varied then the energy of our driving field, then we saw with the strongest driving, we also got a quench, but then after the quench, we got again a strong signal appearing. So if this would have just been a quench due to a high field terahertz drive, the signal would be quenched and gone in the whole time. So this here is something different. And what this really is that here we have a TH signal due to two different orders in the material. Because if you perform the same experiment now with a high driving frequency as a function of temperature, then you can see that our TH signal has clearly two different components. And this first component is a component that disappears when you increase the temperature, while the second component remains. And so this first component is really the superconducting component of the system, while the second component is really THG from driven CDW systems in this material. The question is now, how is this possible that also CDW gives a contribution? And this is pretty simple, because in principle, also any highly driven nonlinear current can generate THG in a system. And to show this, we also switch now into the transient dynamics of the Higgs oscillations. So now we do a terahertz drive experiment, but now we do this with an optical probe. And what you can see here is now basically the pump probe dynamics of these oscillations. So now we are not looking at the generated THG, but at these driven 2 omega oscillations. And what you see here is really now some pump probe dynamics. On the top here, you see now really driven oscillations in this system. And if one analyzes these oscillations, then one sees that we don't have only 2 omega oscillations, but also omega oscillations in the system. And if you look at them as a function of temperature, then you see really these 2 omega oscillations due to Higgs are the ones that really become strongly enhanced below TC. However, you have also omega oscillations in the system that become enhanced. However, at TC, they suddenly become quenched. And these are the ones that we attribute to charge density fluctuations in this material. So in this sense, we see already that the dynamics of the Higgs mode itself gives us new information. However, that is not really transient dynamics. So this is the intrinsic dynamics. And the big question that we wanted to solve is, can we use the Higgs as a probe? So can we really see a transient Higgs response? And for this, we perform now our normal THG experiment. And now we add dynamics to the system by adding an optical pulse. And first here, we just stick to the simplest experiment. We take a 1.5 EV pulse, where we know from various terahertz experiments, Arcus experiments, that this pulse will destroy superconductivity. So it will quench superconductivity. And what we do now is we look at this drive experiment, and we do extend this now into a pump drive experiment. And what we are showing now is this is the generated TH signal without an optical pump. And we are going to look now at the changes of the field at this maximum and minimum of this signal under the optical excitation with an optical pump. And this is what you see. So you really see now a pump probe dynamics. This is now the modulation of the THG signal. And this really reminds of the typical quasi-particle dynamics that one sees in the system. However, in addition, you see here strong oscillations on this. So if you subtract these, then you see this here is something that reminds a little bit on the known quasi-particle dynamics from pump probe experiments. And here we have now oscillations on the onset in the system. And if we analyze them, we see these are oscillations at 2 omega and 4 omega. The second interesting thing is, if you go back here, so on the maximum, the TH signal becomes enhanced. On the minimum, the TH signal becomes smaller on this. That means in principle, it looks like as if we had here an enhancement of the TH. And that is really counterintuitive, because as we said before, the Higgs mode itself, if that would be the reason for the TH and we are suppressing superconductivity, we would have expected that this TH signal should be decreasing. However, here we have an enhancement of this TH. And the question is now, is this really a fingerprint of an enhanced coherence, or is something else going on? And the second puzzle we have to solve, what are these 2 omega oscillations? Because we have already seen in the nice talk from Ilyas before, some of these systems can be due to driving nonlinear currents in the system that cause a symmetry break and then give us something like this. And yeah, so this paper we have just seen in the first talk. So now we have to solve, are we seeing some complicated interferences of driven supercurrents with the pseudospin, or also what is discussed in this field a lot, do we see Higgs plasmon beating in the system, where the TH can not only come from the pure Higgs response, but also from Cooper pair excitations, so charge density fluctuations in this system. And to solve this, we first just perform now fluence and the temperature dependence of this signal. And for first, we ignore these fast oscillations and we just look at these transient changes of the TH signal. And then if we do this at lowest temperatures as a function of fluence, then we see that the stronger we drive, these systems. So this is something that is in agreement with an amplitude problem. And also this goes with the square of the fluence. So this really is driven with the field. And then at a certain critical fluence, we start to suppress the signal. And that is fully in agreement because this fluence is a known fluence because that's the pair breaking fluence for the Cooper pairs that is known from optical experiments. That means the fluences below basically do not break Cooper pairs, but only destroy the phase coherence between the Cooper pairs, and pair breaking sets in only here. And so this is fully in agreement what one would expect now with the pair breaking process as a function of fluence. If we look now at the temperature dependence at intermediate fluence at this 20 microjoules per square centimeter, then we really see that here now driving this with two different fluences, either with a strong or low. Both of these dynamics show something like an order parameter like behavior. However, they go down at a temperature significantly below TC. And if we look at this temperature, this is really the onset of fluctuation temperature in superconductors, and it is, for example, known from linear terahertz measurements like done in Peter Armitage's group and so on. So that means what we are seeing here in the changes of the TH is really something, a function that seems to be susceptible really to the pairing amplitude of the system and going down to the point when there is an onset of fluctuations in the system. However, to get the full information now on this spectrum, we have already seen in the nice talk of Ilias before how powerful the 2D response in such a signal is. And here we are also going now to dissect our signal before into a 2D spectrum, but in a similar but distinct different way as we have seen this in Ilias's talk, because in Ilias's talk we had 2 terahertz pulses, where then we subtracted basically the response of the single pulses. Here we are already probing the Chi3 response because we are looking only at the excited THG signal in our material. So here we have now already the basically filtered nonlinear response, where we look now at the time delay between this TH response and the optical pulse. And with this, we try now to disentangle our pairing amplitude and the superconducting nonlinearities in the system. And this is how such a spectrum now looks like. Maybe the first instructive view here is if we are staying on this pump probe scheme and we're changing the delay, then this looks like here we see this modulation of this TH response in our system, and we see the fundamental does not seem to be modulated strongly. And this is what we have seen as these 2 omega oscillations. And okay, the 4 omega oscillations are barely seen in this color plot. If we now do really the 2D spectrum of this, then we see this here in this 2-dimensional frequency plane. We see the fundamental and the third harmonic in these circles. Then we see this cigar-shaped structures. This is basically the mixing of these 2 signals with our short 100 femtosecond optical pump pulse in the system that has a certain bandwidth, and this is basically what is shown on the dynamics along this diagonal. And what is shown here is that we don't really have a second harmonic generation in our signal. So our second harmonic signal that we saw in these 1D traces comes from these diagonal elements here in this part. This is what it is. And this picture here shows us that this generation of these 2 omega and the 4 omega oscillations basically is a 4-wave mixing signal of our third harmonic generation with the pump photons of the signal. And yeah, if one looks carefully, one can also see that there are also higher order effects here in the red box, giving an additional diagonal signal on this. That shows already now that in principle we can understand these 2 omega oscillations that we have seen as a kind of sideband generation to the GH signal. So I can picture it in a way, for example, we come with our optical pump pulse, we break a few Cooper pairs, they generate quasi-particles, and they now oscillate in our persistent many cycle pulse in this. So that's why we have now a modulation of our TH signal with a signal that is modulating this with omega. So we see now signals of 3 omega plus minus omega, and that gives us the 2 omega and 4 omega signals in this material. So then in the end, we have to see, okay, how do we learn now something really on the transient order parameter in the system? And for this, we really have to look now at the transient spectra. And there we have to now look at these 2D spectra in a different way. So to really get the spectral response, we really have to make sure that these pump pulse and the gating pulse really have always the same time delay when we probe them. So in principle, we have to flip now this 2D spectrum here by 45 degrees in this part. And that is what we have done here. And that is now really the transient spectral response of this system. And if you look at this, then the picture looks surprisingly completely different. Because here you see now when the pump pulse arrives, we see a strong modulation of the fundamental in the system and only a weak modulation of the TH signal. And also here you see there is no second harmonic generation in this system. And to get now the full dynamics of the order parameter, we look now at this transient third harmonic signal, and we have to now correct this in principle, because that's the signal that looked enhanced at the very beginning. We have to correct this now by screening effects, because if we pump the system, the superconducting screening also breaks down. So there is a stronger driving field that can really go into the superconductor and can drive nonlinear dynamics. So to compensate for this, we take now this transient TH signal and divide this in principle by the, by the cube of this fundamental. And then we see here really that our superconducting order parameter becomes quenched and then recovers on a few picosecond time scale. However, due to this modulation of the fundamental, we see here some very curious oscillations in the signal, where some of them even seem to suggest enhancement of the order with periodic modulation. But what is really the correct interpretation of these? This is something we really don't know. So at the moment, we can only present this as an interesting experimental observation. And what we can do now, of course, is to compare this dynamics, which is really now the intrinsic dynamics of the order parameter, with all the dynamics, for example, that is known from the gap dynamics measured in ARPUS measurements. And also we have seen we can distinguish, for example, pair breaking dynamics that would close the gap and fill in close the gap to, for example, the decoherence physics that would fill in the gap in such a material. We have also seen that our order parameter is sensitive to the onset of superconducting fluctuations in the systems compatible with the known spectra in linear terahertz spectroscopy. And the final dynamics of this pair breaking and recovery, of course, we can now start to compare with all the knowledge that was accumulated in the community in the last 20, 30 years, where, for example, Jure Demser has written a very nice review on this, and where one can really now look at the details of this melting and recovery of superconductivity under optical pump pulses. And now we have a new tool in the system. And with this, I'm already at the end of my presentation. So I've shown you that in principle, driving Higgs oscillations with monochromatic multi-cycle high field terahertz pulses gives us a new tool or interesting tool to drive Higgs oscillations in complicated systems like cuprates, where we can really now find external interactions in the system. I just advertised our latest preprint that we can really see this as a generalized Fano resonance and really learn a lot on the interplay now of superconductivity and charge density waves. And going beyond this manuscript, I already showed that some of these features can be also seen in the transient dynamics of the Higgs, both in the dynamics of the THG, but also in the driven 2-omega oscillations. And as an outlook for really bringing these Higgs into the game of transient light manipulated superconductivity, we can use Higgs also now as a probe tool for the order parameter dynamics in pump probe or even 2D pump probe experiments, where we have seen now this complicated interplay with excited quasi-particles and the interesting dynamics of transient order parameter dynamics seen by the modulation of the third harmonic generation. And with this, I thank you for your attention.
Thank you very much, Stefan. As always, great. Would appreciate people. So we have a few minutes for questions, please. Yes, please. Please.
Hello, Stefan. Thank you for nice talk. Yeah, very beautiful result. Yeah, so I have a question about optical pump THG measurement result.
Yeah.
Yeah, you saw this figure C, clear oscillation in the third harmonic intensity.
Yeah.
So is this due to the fact that only the fundamental intensity is changes after the driving, or THG intensity oscillates in time domain?
At the moment, it looks like the suppression is due to the breakdown of screening, so to say. But then these oscillations seem to be dominantly coming from the fundamental. Oops, that is what you see here. If you look at this, there are only very weak oscillations on the TH signal, but there are very prominent oscillations on the fundamental in this part. And that is something that was very surprising for us, because if you look at optical pump probe measurements, so if you look at the transient terahertz spectrum of this, you never see such an oscillatory signal on this pattern. But here we see this, and that is something we've done this with several different fluences on different dopings and so on. And this is a reproducible feature in this that we need to understand. If this is something that is due to the drive in the system, that is something we can speculate. So you have now these, let's say, the excited quasi-particles in the system, but you haven't really, or even you have maybe Cooper pairs that you just break long-range coherence, and maybe now you can still couple to them, and you drive them with a coherent terahertz pulse, and that somehow this forces them back into coherence or whatever, possibly, but who knows? So that is all speculation.
I see. Okay. Thank you very much.
So I think we don't have time for more questions, but definitely people can enjoy. Elias, you have a question?
Yeah, it was just a short one. So we did this calculation and experiments with the coupling between the autoparameter and the charge density wave in A15 superconductors, right? Yeah, and the result of the calculation was something similar to what you're showing here. We didn't pay too much attention to it because, I mean, we published it in the appendix of the experimental paper, but the main thing was that there was also a reversible effect in A15 happening precisely from this coupling after the pulse. I mean, do you see any reversible effects happening here, like new metastable states and stuff like that?
Okay, we can look back through the data, but from our view so far, not really. So we really see only really this quench and the relaxation. And the interesting thing is, this is much faster than what you would see from optical pump probe experiments. So in this part, so this seems to really probe the intrinsic pairing amplitude of the system and filtered from all the quasi-particle dynamics that you would pick up in linear optics in these parts. But no other reversal. So really just suppression and recovery, very similar to what, for example, are the time scales in time-resolved ARPUS measurements, where they also see a quick suppression of the gap and then a rather fast recovery while you still have a lot of hot quasi-particles in the system.
Right. So this is the behavior you expect between the coupling to a charge density wave in the simulations.
Yeah.
So maybe it's a similar thing.
That could be. So we did now do first experiments also on niobium diselenide on these materials, and where we see now also distinct orders between the charge density wave and the Higgs. But the problem is the region of the interplay is really around these 2 Kelvin. So this is a really tough experimental challenge. Right. But we see also the TH response, for example, of the CDW in these systems. So that is something we see, and we see something that looks like a resonance in the superconductor, but it's really difficult for us to see the dynamics of the two because it's just 2 experimental data points.
Right. So this may be the right material to look at, the one that you already studied, right?
Yeah, exactly. But of course, our key interest is always the cuprates, and so that's why now this interplay with the CDW forces us a little bit to go to the textbook examples of this interplay, and then we see, and then.
Okay, thank you very much. Thank you, Stefan.